The end of the universe. What happens after the last star? Today, we're tackling a topic that's both mind-blowing and a bit eerie. What happens at the end of the universe, after the last star burns out? Have you ever looked up at the stars and wondered how long they'll keep shining? Well, pour yourself a cup of your favorite beverage, get cozy, and let's embark on a journey through time. A journey billions upon billions of years into the future. So, here's the big question. When the last star in the universe flickers out, what comes next? It's a question that takes us to the farthest reaches of both time and space. In today's video, we're going to explore the life cycles of stars, the different eras the universe will go through, and the ultimate fate that might await, well, everything. Ready? Let's dive in. The life cycle of stars. First up, let's chat about stars, the glittering celebrities of the cosmos. Birth of stars. Stars are born in vast clouds of gas and dust called nebulae. Imagine these nebulae as stellar nurseries. Over time, gravity pulls the gas and dust together. It's like rolling a snowball downhill, it just keeps getting bigger. As the material clumps together, the pressure and temperature at the core increase until nuclear fusion kicks off. And voila, a star is born. The main sequence. Once a star is born, it enters the main sequence phase, which is basically the longest and most stable part of its life. Here, stars fuse hydrogen into helium, releasing energy that makes them shine. The bigger the star, the hotter and brighter it is, but that also means it burns through its fuel faster. Massive stars might only last a few million years. Smaller stars, like red dwarfs, can shine for trillions of years. Crazy to think about how varied their lifespans are, right? But all stars must die, and their deaths are as spectacular as their lives. Low to medium mass stars swell into red giants as they exhaust their hydrogen fuel. They shed their outer layers, creating beautiful planetary nebulae, and leave behind a white dwarf, an incredibly dense, dim object about the size of Earth. Massive stars go out with a bang, a supernova explosion. This explosion is so bright it can outshine entire galaxies. What's left behind can be a neutron star, an object so dense that a teaspoon of its material would weigh billions of tons, or a black hole, where gravity is so strong that not even light can escape. To give you an idea of the timescales, massive stars live for millions of years. Sun-like stars around 10 billion years. Red dwarfs can last upwards of trillions of years. It's a cosmic timeline that's hard to fathom. The Stelliferous Era. Now, let's talk about the era we're currently in, the Stelliferous Era. Stelliferous basically means full of stars, and that's what our universe is right now. This era is expected to last for up to 100 trillion years. We're literally in the universe's golden age. But here's the catch. The gas and dust needed to make new stars won't last forever. Over time, star formation slows down because there's just less material to work with. Stars are the engines of the universe. They create heavier elements, influence galaxy formation, and enable the possibility of life. Without new stars, the universe begins to lose some of its sparkle, literally and figuratively. The Degenerate Era. After the last star burns out, we enter the intriguingly named Degenerate Era. This era is called degenerate, not because the universe goes wild, but because it's dominated by degenerate stellar remnants, objects supported by quantum degeneracy pressure. The main players now are white dwarfs, cooling remnants of low to medium mass stars, brown dwarfs, objects that were too small to start nuclear fusion, neutron stars, ultra-dense remnants of supernovae, black holes, gravity wells from which nothing can escape. Over unimaginable periods, white and brown dwarfs will cool down and become black dwarfs, cold, dark, and virtually invisible. Now, here's a mind bender. Some theories suggest that protons might decay over extremely long timescales, like 10-34 years. If that's true, then eventually, all matter could dissolve into radiation and subatomic particles. The Black Hole Era. Next stop, the Black Hole Era. With most matter gone or converted, black holes become the last titans standing. They hold whatever mass is left in the universe. But black holes aren't forever. Thanks to Stephen Hawking, we know they can emit what's called Hawking radiation, losing a tiny bit of mass in the process. Over ridiculous timescales. Think 10 carat, 100 years or more. even the biggest black holes will shrink and eventually evaporate. When a black hole evaporates completely, it might release a final burst of energy, a last hurrah before fading into oblivion. The Dark Era, cue spooky music. The universe is now a vast, empty expanse. No stars, no planets, no black holes. Just a thin soup of photons, neutrinos, and other tiny particles. Entropy, a measure of disorder, is at its maximum. There's no gradient to exploit for energy, so no processes can occur that require it. Without energy differences, nothing happens. It's a cosmic standstill. It's a bit somber, but the universe will be a dark, cold place. The adventure is over. Theories on the ultimate fate of the universe. But wait, there are alternative endings to this cosmic story. We've covered heat death, where the universe reaches thermodynamic equilibrium. No energy flows, no life, nada. Similar to heat death, the Big Freeze suggests the universe keeps expanding, temperatures approach absolute zero, and everything becomes isolated. Once upon a time, scientists thought gravity might stop the universe's expansion and cause it to collapse back into a singularity, the Big Crunch. Recent evidence suggests the expansion is accelerating, so this one's less likely now. Enter the Big Rip. If dark energy increases over time, it could eventually overcome all forces, tearing galaxies, stars, planets, and even atoms apart. This could happen in about 22 billion years if certain models are correct. Structures get pulled apart, starting with galaxies, then solar systems, then atoms. Now for the wildest of them all, vacuum decay. Our universe might not be in the lowest possible energy state. Think of it like being in a valley that's not the deepest one around. A random quantum event could create a bubble of true vacuum. This bubble would expand at the speed of light, altering physics as we know it. Definitely bad news for everything inside it. Philosophical and scientific reflections. Phew, that's a lot to take in. Let's step back and think about what this all means. Understanding these cosmic finales can make our everyday problems seem small. But it also highlights how special our moment in time is. When we're dealing with numbers like 10 carat, 100 years, it's almost impossible to grasp. Could intelligent life survive these endings? Some theories suggest advanced civilizations could harness energy in ways we can't even imagine, or perhaps find pathways to new universes. At the end of the day, exploring these ideas fuels our curiosity and drives scientific discovery. Who knows what we'll learn next? So today, we've traveled from the birth of stars in nebulae all the way to the dark, silent end of the universe. It's been a wild ride across trillions upon trillions of years. While the eventual end might seem bleak, there's beauty in the journey. The universe is dynamic, filled with wonders at every stage. Thanks for joining me on this cosmic adventure. If you enjoyed this video, smash that like button, subscribe for more explorations of the universe, and share with your fellow space enthusiasts. What do you find most fascinating about the universe's future? Let me know in the comments below. Until next time, keep looking up and stay curious.